Let us verify Lagrange mean value theorem for the function fx equal to 1 by x in the closed interval 1, 2. So we are given fx equal to 1 by x in the closed interval 1, 2. And we want to verify Lagrange mean value theorem. If we want to verify Lagrange mean value theorem, we need to make sure that a number of criteria are satisfied, exactly 2 of them. First one is f has to be continuous. Is this function continuous? You see that 1 by x, that's the quotient of two continuous function, one continuous function divided by another continuous function, and quotient of continuous function are continuous provided the denominator is not equal to 0. But we are taking x greater than 1 and less than 2, so x cannot be 0, so denominator is not equal to 0, so f is continuous. F is continuous on the closed interval 1, 2. Remember, we are taking x greater than 1, so 1 by x, we were making sure that denominator is not equal to 0. Again, is the function differentiable? The second criteria is we need to make sure that f is differentiable. Yes, f is differentiable. F is differentiable on the open interval 1, 2. We don't need whole of the R. We don't need to show that f is differentiable throughout R. Once again, it's a quotient of two differentiable function. Fx equal to 1 is differentiable, fx equal to x is differentiable, and quotient of two differential function is again differentiable provided denominator is not equal to 0. So we are taking x greater than 1 and less than 2, and in that case f is differentiable. So we find that f is continuous, first criteria is being satisfied, and second we find that f is differentiable, so second criteria is satisfied. So Lagrange mean value theorem is applicable. In other words, we can apply Lagrange mean value theorem. What does Lagrange mean value theorem says? Lagrange mean value theorem says if f is continuous on the closed interval a, b, differentiable on the open interval a, b, then there exists a constant c such that f dash c equal to fb minus fa by b minus a, and that c must lie on the open interval a, b, that is, c must be greater than a and less than b. Now in this case, we found that f is continuous on the closed interval 1, 2, differentiable on the open interval 1, 2. So a equal to 1, b equal to 2, and there must exist a constant c such that f dash c equal to fb minus fa by b minus a, and that c must lie between a and b. So we should be able to find a constant c such that f dash c equal to, by Lagrange mean value theorem, there exists a constant, c such that f dash c equal to fb minus fa by b minus a. What is fb? f2. f2 minus f1 by 2 minus 1. Now fx equal to 1 by x. If you differentiate it, we'll get minus 1 times x to the power minus 2. So fx equal to x to the power minus 1, that is 1 by x. If we differentiate it, then we'll get f dash x equal to minus 1 x to the power minus 2. So f dash of c equal to minus 1 by c square. So we should be able to produce a constant c such that minus 1 by c square equal to f2. f2 is 1 by 2. f2 is 1 by 2 minus f1. f1 is 1 by 1, that's just 1, divided by 2 minus 1. 2 minus 1 is just 1. That is minus 1 by c square must be equal to, well, half minus 1 is minus half. So minus gets cancelled. So if we cross multiply, we get c square equal to 2. That is, c must be equal to plus minus root 2. Is root 2 lying between 1 and 2? Of course, minus root 2 doesn't lie, but root 2 is definitely greater than 1 and less than 2, because root 2 equal to 1.414. That's greater than 1 and less than 2. So we have determined a constant c equal to root 2, that lie between 1 and 2, and f dash of root 2 equal to f2 minus f1 divided by 2 minus 1. So we have verified Lagrange mean value theorem for the function fx equal to 1 by x in the closed interval 1, 2.